Now I wanted to start to talk about the first order low pass filter. So we saw that if we have in the ideal low pass filter, we want to design a filter that let the lower frequency pass through and the higher frequency be rejected. So if that is the ideal one, now I want to see how practically I can design a low pass filter, and this is going to be the first order low pass filter. So it's going to be the analog filter. So assume that I have a resistance like that, and then I have a capacitance like this, and so they're in combination like that. So let me extend that, extend that. So assume I have a circuit like that. So I have a R here, and I have a C here. So it's going to be the R, and it's going to be the C. And let me draw these comes here and draw these comes here. So if I come and consider this part of this, I just put it, for example, assume I put it in the box. So if I put this part, is the R and C in one box. This box here, whatever is represented here, is going to be the first order, is going to be the first order low pass filter. So that circuit here, that simple circuit here, the circuit that's combination of the R and C as this, is behave as a low pass filter. So if I go, so if these two are the input for that filter, and these two are the output for that filter. So if I go ahead and, for example, assume I connect any signal to that, the input signal to that. So that's going to be the input signal, and it can be any signal. So I have an input signal to that, connected like that. If this is, I connect this input signal to that filter, then here, whatever signal I'm gonna get out of here is gonna be the output signal. It's whatever is filtered out. So if I put the input signal here, it goes through this box here, this low pass filter, and the lower frequency would stay as much as possible untouched. The higher frequency would be rejected as much as possible, and then I'm gonna get the output of that or the filtered version of the input signal as an output signal. So if we look at here to work with that, first of all, so in this circuit I have here, I can say it has the equal impedance. So I have the R, I have the C. So this Z equal here, the equivalent, let me write here, the equivalent impedance for this circuit, for this RC circuit, is the Z for the R is impedance of the R plus the impedance of the C, because they are in the series. The R and C are in series, so we just add their impedance together. And we know that the impedance of the R is just simply R, and the impedance of the C, we know that is negative J divided by omega C. So we know it's gonna be like that. So this is the impedance of the C. So if I add these and then also I know that, so let me write here, the ZR is just R, the ZC is negative J divided by omega C. That, or also we can write it as a 1 over J omega C. We can write it either of these way, and the omega is 2 pi f. So we know that if I combination these three and put them together, and let's write this in this way instead of that. So instead of having this, let's have it as 1 over J omega C. So it's going to be R plus 1 over J, and for the omega I put 2 pi f. It's 2 pi f, so it's the omega, and then it's going to be the C. So it's let's make sure you know that's a omega. So this is the equivalent impedance for this system. Now that I know that for this system, I can go ahead and let me write it here. So I know the I. If let me say where is the I. So if I have the I goes through this circuit, so here, assume I call it, or let me choose another color. So whatever in this one's going to be I. So we know that if we are working with impedance, we have this equation of the V is equal to V is equal to IZ. That equation we have is similar to Ohm law. So I can go ahead and say in this case the V as the input voltage here is equal to the I times the Z equivalent to this, the Z equivalent to this one. So if I add these two, it's going to be simply one element. So it's going to be a very simple circuit here. So I'm going to just draw it here. So I have the V input, then I have this Z equivalent here, and then I have these two output terminal. So, and then this is the I going through this one. So it's going to be very simple. V is equal to this one. So therefore, if I go ahead, the I is going to be the V input, and for the Z equivalence, I can put this value here. So it's going to be R plus 1 over J 2 pi omega C. So this is this is going to be the I that we want. Also, I'm going to rewrite it as a Vn as well. So because we need it later on. Also, the Vn plus this one is going to be I that times this. So it's going to be R plus 1 over J 2 2 pi omega C. So it's just this equation, but just write it in two different ways because we need both of them later. The output signal, I can write this the same equation here, also for the for the output, but here. So if I write again V is equal to IZ, then the V out is the same because this is connected. This port is connected to one end of the C. This port is connected to one end of C. the voltage at this output is the same as the voltage at the capacitor here. So whatever is the voltage of capacitor is the voltage of these two port on two output port. So they have the same voltage. Therefore, it's going to be I, and then it's going to be Z, C, whatever the Z of that C. So then the V out is going to be the I, which is this one, and the C is going to be this here. So it's going to be also I'm going to just write it here in case that it's going to be J 2 pi omega C here. Let me write this little bit here. So it's going to be V in. And so the ZC is going to be 1 over J 2 pi omega C. So this is the output filter. And if I just replace the I from here, I can go ahead and say that the V output is, this is the I, this is the I here, is V input divided by R plus 1 over J 2 pi omega C multiplied by 1 over J 2 pi 2 pi omega C. Sorry, 2 pi F 2 pi FC. So I have to change. So all this omega is F. So this is the F, and this is the F here. This is F here. This is going to be F here. So it's J2 pi FC is J2 pi FC. 2 pi FC and then 2 pi FC. So I hope everywhere. So this is the input and it's the output that we have. Now go to the next page. So we know that the for the filter for the transfer function of the filter is just the output signal versus the input signal. So we know that's the transfer function of filter. So if I go ahead and we put this V in and V out in that equation, just substitute these two in that equation, what I'm gonna get, if you put it there and simplify that, what I'm gonna get is gonna be eventually it's gonna be 1 plus J 2 pi F R C. So that's what I'm gonna get eventually. And if I go ahead and say FB is equal to 1 over 2 pi RC, well, if I call it write that, and this one, this is gonna be my here it's called it the breaking frequency, but it is that similar to that cutoff frequency that I talked about it in ideal for the ideal filter. So you can consider it as that's the cutoff frequency. So that's the frequency that you want to let all the frequency before that pass through and all the frequency after that to be cut off. Or also they might you might say they call it the break frequency as well. So that if I call that FB is 1 over 2 pi RC, which is going to be the frequency that I want to be my cutoff frequency. In other words, I want to be everything is less than the FB pass through, and everything larger than FB is going to be removed. Then I can go ahead and uh, write the HF, or the transfer function of the filter, as 1 over 1 plus J F divided by FB. Oops. So then it is gonna be the uh, first order low pass filter. Or I can go ahead and write that this one. Also, I can write it in form of, so this is in the rectangular form. It has a J. I can go and also write it in the polar format as well. So I can say that also the HF, if I convert it to the polar format, because it's the complex number, I can say that it's going to be, it has a magnitude of 1 over 1 plus F over FB square, and then the root square of that with the angle of tangent inverse. So sorry, it's a negative tangent inverse of F over FB. So either I can write it as a rectangular form like that, or I can write it as a polar format like this. So this is how I can write the low pass filter. So in other, if I want to mention that, so what we have is the first order low pass filter. So it's a low pass filter, and it's supposed to pass the lower frequency, let the lower frequency signal pass through, and it's supposed to filter out the higher frequency. So if I go ahead and plot this here, so if I go ahead and say, if I'm going to plot this, the magnitude and the angle of this filter here. So if I say it's going to be the magnitude of HF with respect to the frequency, and then it's going to be the angle of that HF. So it's going to be the angle of HF. Here I plotted as a frequency here. So let me just mention, so this part is the magnitude of the, if you remember it from the complex number, this is the magnitude, and this part, the second part here, this part here is the angle of the HF. So so the so if I plot the first part and this second part of that here as a function of the frequency, let me bring this a little bit higher so they look the same. So if I plot these two and see what I'm going to get. So if I start it from here, for the magnitude is gonna have, it's gonna look like something like this. And for the angle, it's gonna look like something like this. So this one is gonna be 1 here. That's 1, and then eventually this is 0. And here is the angle, here is the 0, and this here is negative 90. So it goes from 0 to negative 90. It goes from 1 to 0. So as you can see here, and then that f, the cutoff frequency is going to be somewhere here. So it's going to be the cutoff frequency. And for this one, it's going to be, for example, the cutoff frequency. So basically, if you can see that, especially in this part of that, is if you see this filter is going to change both the magnitude of the input signal and the phase of the input signal. And if you look at this, you would see that. So let me bring this a little bit to the right. So there looks like the same. So I assume this is the FB. So especially if you look at this part of the signal, you will see that when we are dealing with the lower frequency, it doesn't change it that much. It's very close. The magnitude of the filter is close to the 1. So it tried to not touch the lower frequency, and then it tries to reject the higher frequency. The same here for the phase, it tried to reject the it tried to not change the lower frequency, and then it's changing the higher frequency. Compare this to the ideal filter, so I just draw it up here. So if I draw the let me see if I can draw it down here. So so if I working with the, so for the ideal frequency, and if this is so for the ideal low pass frequency, we had something like that. So it goes here when we get to that, and then it goes to 0. So this is the FB, and let me put it somewhere. So this frequency here, so here is the FB, and this one is the ideal low pass filter. So you see that in the ideal filter, we want to go from 1, suddenly drop to 0. But in the real world, practical one, when we have the first order, there's going to be the continuous curve goes from the 1 to 0. So we want to keep the curve close to the, when the curve is less than the breaking frequency, close to 1, and when the curve is goes past the cutoff frequency, we want to bring it as close as possible to 0. So you will see that there's a way difference between what we have here and what we have in the ideal that we want to get. Later, we are not going to discuss them, but this is what we have. It is the first order. We can go to the higher order filters. So we can make this as much more closer or much more look like this one here. But for now, um, when we are dealing with the first order, that's the best we can get uh, between these two. Similar to the first, similar to what we have here, also we are gonna have the uh, the high pass filter. So this one was the uh, uh, first order low pass filter. So also we can have the first order um, high pass filter uh, as well. So I'm gonna show you that. So first order high pass filter. So similar to what we have for the low pass filter, we can have it for the high pass filter. Again, this time, um, um, assume the previous time we have the resistance and the capacitance. Now we are going to just switch their place. So assume I have the um, assume I have the capacitance sitting up here, and then it goes to resistance here, and then it goes and then goes out here. So if I have a C, I have a C here and I have an R here, and then I put them in the box like that. That circuit here inside that box is gonna be the first order high pass filter. So first order high pass filter. So if I go ahead and then, for example, if I connect any input signal to that filter, and assume I'm gonna, for example, connect the input signal to that. So if I connect it to the input signal to that circuit like this, then whatever I'm gonna get here is gonna be the the signal is gonna be filtered out with this circuit, and then I'm gonna get the signal that is filtered out at that. And this is going to be the high pass. Remember the high pass? The high pass filter is a filter that's supposed to let the filter with higher frequency pass through and then remove the frequency that has um, the signal that has a lower frequency. So I'm not going to go through to how we can drive the equation, but I just simply write it here. So that high pass filter here, which is basically the V out versus V in. So that one is going to be, can be, if you do the calculation, is going to be J F over FB. Again, the FB is the cutoff frequency. And then it's going to be 1 plus J F over F B. So it can be written as that in the rectangular format, and as I said, it's because it's a um, what do you say? Because it is complex. Also, I can write it as the polar format, which if I write it as a polar format, is going to be, let me write it a little bit lower. So polar format, it's going to be, the magnitude of that is going to be F over F B, and then divided by 1 plus F over F B squared, and then a square root of that. And the angle is going to be 90 minus tangent inverse of F over F B. So it's going to be, either you can write it here like that, or you can write it like this here. So either of them we can do that. So if I go ahead and again to draw this one, the magnitude, which is going to be this part, and the angle, which is going to be this part, if I draw them to see how it's going to be look like. So if I go ahead here and draw, let's come a little bit lower. So if you draw the frequency and then the magnitude of that filter, and it's going to be so it's going to be its magnitude respect to the frequency, which is usually going to be the hertz. And let me draw it a little bit further. And then if I draw also the angle, the phase as well. And so this kind of, the second one is going to be the phase of the HF. So the first graph is shows this part, and the second part graph shows this part, and then I go ahead and plot them. So it's a high pass filter, so it's supposed to reject the lower frequency and let the higher frequency pass through. So if I go ahead and draw that, it look like something like this. So it goes up there. So it goes up there, and then eventually goes towards 1. So it's in case of the, so this magnitude is 1 here, and it's going to be 0 here. And then for this part, it goes from here, something like that. So it's going to be 90 degrees here, and it's going to be 0 here. And then we can say that the cutoff frequency is going to be, for example, somewhere here, assume. So it's going to be the cutoff frequency, and the same have it, for example, somewhere here. So it's going to be the FB. And again, remember, I'm going to just write it here. The FB is the cutoff frequency, and it's the same as before. It's going to be 1 over 2 pi RC. So is the break or cutoff frequency. As you can see, when we design this filter, we want all the frequencies above the cutoff frequency to pass through without any change, and all the frequency below the cutoff frequency to be completely rejected. So if I draw the ideal, just draw down here the ideal high pass frequency, see what's the ideal one, and what we get actually is that in the ideal one, so it goes, the high pass frequency goes to the FB, and by the time we get to the FB, it goes up here. So it goes up here, and then this stays 1. So it's going to be 1 here, it's going to be 0 here, and this is going to be, so this is the ideal high pass filter. And this is going to be the FB. So as you can see here, this is what we, in the ideal world, we want to get into that, but this simple filter, the first order filter, gives us this. Again, if we go through the higher order filter, this is the first order. If we go to the higher order filter, we can get the filter that's much closer to this one. Also the same as the phase, you can see it tries to leave the phase of the input frequency untouched for the for the frequencies or the signals that are larger than the FB.